All right, 4 o'clock. Let's get this started. All right, everyone, thank you for coming. This is a great turnout. We're super excited to be giving this talk for you. And to actually kick it off, we want to do a live demo. So you guys can follow Ryan Onrock here outside for a demo. You could leave your things here. I'll be here to stand guard. But love to show you a demo first. So after the demo, we're going to have pizza set up on the mezzanine level, so you can grab some pizza before you come back in to before we start the talk. Right, sound good? All right.
Do you know if they're recording?
Yes, they are.
Oh, great.
All right.
Cool, thank you.
Are you just coming in?
Yeah.
Yeah, so they're doing a demo over there outside.
Oh, okay.
Yeah.
blocks away. It's relatively quick.
Okay.
But it was good.
The demo is done?
Yeah. The pizza's almost here.
Oh, okay, cool.
Yeah.
That was fast.
It was pretty fast.
You guys just ran around?
Kind of, yeah, around the trees. But yeah, it was good. It showed it off.
Also pass it around a little bit. That sounds really good.
What's that?
You can also pass it around a little bit if you want to see it.
Yeah. Yeah, that's a good idea. Keep an eye on the pizza as we come.
My suspicion is that instead of saying, "Oh, I can't do it," I know it looks like a plan, but trust me, this is some guy. But you're right. I share your suspicion. Make your life a little nicer. But yeah, basically it was just a straight up. How did your
I'll do an intro and play the launch video. I'll do an intro and play the launch video. Hey everyone, hold on. Hey everyone, does that work? Testing, okay. So the pizza is being set up. And I'll give a quick intro and play a video, and then by that time it should be ready, and we can grab some pizza and I'll continue with the talk. So to give a quick intro though, I'm Ryan, this is Anurag and Nancy, and we're from Skydio, and in case you're not familiar with us, we build autonomous drones. We're based in Redwood City, and we just came out with our latest product, as you saw with the demo, a couple months ago, so this is a pretty new product, and I'll start out with this. Oh, it's not even up. This is always fun.
It probably timed out when we were demoing.
Maybe. Let's see. Here we go. It's now connected. And now it will take, of course, like 10 seconds to come up here. There it is. All right. So this is our launch video. I'll just let it play. Oh my God. Well, it goes in and out, though. Like it was.
Yeah, we tried it before.
That. Okay, so it's connected, and now it'll come up in just a minute. Oh, now it's not connected. Okay, that'd be wonderful, yeah. This may be. Should I let you go, or should we just get things first?
Let's try the video again.
All right, I'm gonna try the launch video one more time. See how this goes. Oh, no sound. Oh, good. Okay, we're gonna try a new connector. All
All
right.
right, we're in business.
Oh, maybe it's orange. This is. No touching it. Thanks. And as this notes as well, it's, and I'll go into it in a little more detail, it's also going to be a lot useful for a lot of commercial applications. But we're going to talk about some more of these details after you guys get pizza in just a couple minutes, right? Is the pizza set up? All right, get some pizza, and then we'll be back here in 5 minutes. I think it might be the porch, I'm suspecting, because I'm going to move it over here, because I don't think we need sound anymore.
Oh, yeah. Except the last video with the math's daughter, but you don't even have to show that.
Oh,
Yeah, the
okay.
cutesy one.
Hey, CJ. Hey, it's good to see you. How are you?
I'm good. How about yourself?
Good. It's been a long time since I've been back here, so it's nice to be back.
It does feel that way.
So far.
But no, but congratulations on product launch. It's like we've been watching with bated breath. It's really,
Yeah,
really
it's been
impressive.
very exciting. Yeah, yeah, it just like works way better than the last one, and it's a lot cheaper, and so it's been pretty exciting. See it kind of all come together a little bit.
No, excellent. Yeah.
Yeah.
Yeah, we heard that you guys are also doing some military related, which looks like a really cool application.
Yeah, I think that could be really neat. Yeah, yeah. I think a lot of commercial applications, and that's like inspection or like reuse and infrastructure. A lot of interesting applications. Working on it for sure.
Very sweet. So I guess you're going to go through the tech specs of this and the sensor profile. Or?
Yeah. Oh, I don't know if we have like that in there.
Okay.
I don't know if I know it. So I mean, I could tell you as much as I know.
Oh, just the roughs. I mean, it's still just completely vision based, which
it is. Yeah. So yeah, in an IMU, there's GPS for like the harder situations. But yeah, so these are now fisheye like I guess I'll talk about this in the talk. But fisheye 200-degree field of view, color rolling shutter cameras, which is some interesting challenges to deal with.
No, but yeah, I mean, I guess the entire world is rolling shutter these days, so it makes it easier. Source parts. Yeah,
exactly. Yeah, it makes it. We can get higher resolution color with the challenge of then you have to deal with rolling shutter. Yeah.
Still, that's so cool to be able to do it in that kind of form factor.
Yeah, I think that and now we have fisheye cameras, and so that makes it's a little different than having mostly rectified like linear cameras. It's a lot different field of view. Right,
and they're completely separate and apart from the payload camera.
They are, yeah. Yeah, this has another challenge. This now has a
gimbal.
A 3-axis gimbal, so like yaw, it's in there too.
Yeah, but this isn't used for nav. It's just used. You just stabilize.
Yeah,
it
exactly. Yeah. It's just used for taking video.
Yeah, and, previously guys you were using like a TX1.
Yeah, it's a TX2 now.
It's TX2, yeah.
A little more powerful.
Yeah, we like those a lot. The Xaviers that they come out with also pretty power hungry.
Yeah.
But
I don't know too much about them, but
excellent. You get what, a 15, 20-minute flight time of this, or
23.
23. Wow, that sounds good. Yeah, because this feels like what, kilogram and a half, right? Oh yeah.
Really just a battery holding itself up.
23, yeah, that is very sweet. Excellent. So
Pretty fun. Yeah, how are you doing?
good.
I had a couple of students, we were at the career fair today,
Right.
and a couple of students that were in your class, I guess, stopped by, which is neat.
Yes, we sent them all in your general direction, so to get a sense of what's happening. No, things are going well. So doing a lot of kind of distributed robotics stuff, looking at ground air, but still, planning, recognition, coordination, things of that nature. So, and still doing some flight stuff. So, but we're working on it. I don't think you guys didn't have a chance to go over to Innovation or.
No.
Okay. Yeah, we're we have one of the platforms we're working on, just sort of a larger LiDAR-based one. So.
Okay.
So yeah, it gets the pluses and minuses of LiDAR.
Sure.
Second? Yeah, so there's dam inspection that we're also using now for other stuff. So we're doing like flying in among trees. So there's actually a small spin-off we have that's doing this for actually accurate measurement of tree diameters.
Okay.
So we have to have a pretty accurate 3D map of the environment some semantic localization on top of that. So, so that's one thing that we're looking at is kind of with the new breed of like Auster LiDAR systems, which are interesting because you get big read, which also get back an intensity signal. So gives you some ways of, so we're looking at kind of ways we can combine, get the best of both worlds to pull it, to treat your LiDAR like a camera. But it has
requires a lot of power, does it? Or?
Less than you'd think, and it's down to like 650 gram, so it still means that our platforms end up being bigger.
Yeah.
But the military hates anything LiDAR related. So doing it all with
Why do they hate LiDAR?
Well, because it's like putting a bright shiny light on your head and saying, "Please shoot me."
Okay.
So that's not their favorite thing. So I think vision based is really the way that really a good way to do it.
Yeah.
So that's another thing actually. We've been working on this. We'll see if we can do some of this stuff for binocular.
Yeah, it's pretty. At some point, like if you make it small enough, you don't have as much stereo baseline at all.
Exactly. So that's so from a research standpoint, that's another thing that we're looking at. So can we get that? Down and back to the we get us to smaller size platforms. But wow, this is amazing. You're doing work on the
Yeah, I do like the 3D mapping. Obstacle board. Try to make it not hit things.
right.
Which is move like more deeper. Which is been fun. It's been a pretty powerful tool. Working well.
Wow.
And it allows us, I think, like a lot of room to improve it. When we were using SGM and like more classical things on the previous drone, like at some point it's like I don't know what to do to like improve this, but like with deep learning, I feel like I have like tons of ideas that I can improve the data or improve the loss function. Or there's a lot of ways to improve it that I couldn't before.
Yeah, I mean, one thing that we've been doing that might actually be is because we can now in a position where we can capture both stereo, but then timestamp it with the LiDAR. Yeah. So we have a bit more. So
it's powerful.
Yeah.
One of the big challenges is like how to get good data for it.
Precisely. So that's one of the things. Ian, for instance, done something in that regard. So that might be something that we want to talk about if we could. We wanted to get that data for our own purposes. It's going to help somebody else.
Yeah, definitely.
I should.
Okay. Yeah.
Testing. Okay. Oh, that works. All right. All right, we're going to get started, I think. Wait till the last few people sit down. You guys ready? All right. So thanks for coming. Hope you enjoy the pizza and the demo. We're going to talk a little bit more about how we make this happen. First of all, I want to, touch on how we're different than some of the other drones that have been out there. There's been a lot of commercialized drone applications. Some of them get a lot of press, from selfie drones to delivery drones to drones for inspection and other automated things, or for sports filming. Until now, when you go outside, you don't see drones flying around everywhere, though. So until now, they haven't really lived up to that potential, even though it's been really easy to imagine, because they've been difficult to use. And so that's ended up in a lot of the reviews of these different drones. On the top left, any suggestion that we're getting close to a point where drones are as easy to operate as, say, an iPhone is woefully overstated. So they're just too difficult to use right now. On the top right, talking about delivery drones, and then when you get closer to the destination, you're going to have to deal with obstacles and being able to do that effectively on these platforms has been difficult. On the bottom left, again, similar things for inspection applications, that many of the most innovative applications aren't really achievable with drones until you have full autonomy and can trust it without an expert pilot. And then some have even gone farther than that, and on the bottom right, a drone company that intentionally misled consumers with promotional videos that exaggerated their performance. So why has this happened? I think it's because it's very difficult to have true autonomy. And so that's what we've been trying to deliver with now the Skydio 2, which has so far received some great press. The top right quote here, robots aren't supposed to be this good, from IEEE. The way we've done this is with an incredible team on both the hardware and the software side. So we built this drone from the ground up with people from across the board of great institutions. We think the key here is that having full autonomy and really being able to trust the drone unlocks the full potential of drones and allows a lot of these use cases that until now have just been in people's imagination to actually occur. And this kind of gives an idea here of the difference between having full autonomy and having some autonomy, which is what we've kind of had until now. So this is just a comparison of an ATV ride between the Skydio 2 and the Mavic 2. And so both of them track fine, both of them have some obstacle avoidance, but if you just have some obstacle avoidance, then you can't really plan a great route around difficult obstacles and get cinematic video of your target. And so having autonomy above some level allows you to have a lot of these different applications. And so beyond user and consumer use cases, there's also a lot of enterprise use here. So this is an example of the dock that we've built. So we're going to be working with different commercial partners, and the idea here is to enable even further autonomy and not only be able to launch a drone and have it do something, but have it be persistent in that it can land in the dock, charge itself, and continue without any human intervention. So this opens up use cases for example, scanning construction sites autonomously and coming back and then being able to do that again and compare against different time frames without having a human in the loop at all. And that opens up a lot of these opportunities. Here's another really neat example of inspection. So this is something that would be, I think, basically impossible with anything else, even with an expert pilot. So this is a bridge that we want to really get up and inspect in this tiny passageway where the pilot doesn't have good visibility at all. But by having 360-degree obstacle avoidance, so on the left here it's showing the drone's cameras. The top three cameras here are facing downward, and then on the bottom, they're facing upward, and on the bottom, these three cameras are facing downward. So it has 6 cameras that give it full surround view. On the right, it's showing the 3D map that's being built by the drone. And so you can see it sees these different poles that are part of the bridge and is able to plan a path even in this very tight space and get video of inspection that otherwise would be pretty unachievable. This is a really neat video that I'm going to come back to a couple times in the talk, just showing the kind of predictive power that autonomy also allows. So here we lose the subject. It's going to loop, so I'll show it again, but we lose the subject, but by being able to have a full 3D understanding of the scene, know where the subject is going, and then also predict that into the future, we can plan a path all the way around these obstacles that's still smooth and cinematic, but that catches up and creates a really neat video. So this, again, is fully autonomous. There's no one actually flying the drone. All these decisions are made online on the drone as it flies. So how we do this, there's a lot of different pieces of the system. I'm going to touch on a few in this talk, but to give a general idea of the different pieces that go into this. First of all, starting on the left, the drone has to know where it is. So that's this visual inertial odometry. Basically, it's tracking points in the world, and based on where those points are, it can tell where it is. Then we want to eventually get to a dense depth map, and we do that with a couple different things. First of all, semantic segmentation. So this is the drone takes the camera images and uses some neural networks to figure out what things are around it. So whether it's trees or sky or other objects in the world, it gets a sense of what its environment is. From the different cameras, we can also compute a dense depth map that tells it how far away things are. Then given these two, the drone knows where it is, so it can project these points out into the world and build a 3D map of the world, which is shown here at the top left. So now the drone knows where it is and what is in the world. It has to figure out what to do. So most of the activities of the drone are based on the user camera on the front. In order to use that, we need to have gimbal estimation. So the gimbal here at the front of the drone, it's a 3-axis gimbal, so it has roll, pitch, and yaw. And it has to estimate online, so it uses visual estimation to basically map the image from the subject camera into the nav cameras and align them, and that allows it to know where that user camera is. Then based on the user camera, we can detect objects, people and cars and other objects, and also do multi-object tracking, so we can distinguish between different people. Once we have that, we need to figure out what we want to do with it. So this feeds back into the user interface from the app, which in different modes can allow the drone to have different behaviors. Then once the user tells the drone what it wants to do, we have a motion planning system that takes all of this information, plans a good path in order to achieve it as well as it can, and then feeds that to controls which try to achieve that plan by spinning the motors in order to achieve that path. And so then this feeds back in the next time step. So this is kind of a loop with a lot of different pieces, and they all interact together. And if any one of them fails, then you're going to have a lot of difficulty. So some of the pieces of how this works. So this is just showing some of the images themselves. These are one top and one bottom camera on our drone, and these are 200-degree field of view fisheye cameras in their color. So we have 360-degree view all around the drone in full color. And what that allows us to do, first of all, we can look at it in a different space. So this is a panorama view where we know where the cameras are, we know where the drone is, so we can take these cameras and project them into the world and stitch them together into a panorama. The yellow square here is also showing where the subject camera is at this time. So the subject camera is looking at the person, and we know exactly what it's looking at. And this is the same clip that we saw before, the mountain biking. So given this, we want to create a 3D map of the world. Just to give kind of a general idea of how this works, we have our cameras which are fisheye cameras, and those are a little bit difficult to deal with. So one simplifying assumption you can make is to turn them into rectified stereo cameras. What this means is that if you look at any pair of cameras, an object in the world is going to project into the same row. So if you want to figure out where this person is, you just kind of look along the same row, and if you get good matches, then you can project those into 3D and figure out where the person is in space. So this gives us, on the right here, some estimate of the depth map. This is showing a bit old of a depth map, but the same idea applies to any modern algorithms like deep learning based, where we have some estimates of depth, some are going to be better than others, and so we want to be able to figure out which ones are bad depths and filter those out. So on the right, this is showing a filtered depth map where we filtered out any of the bad stereo pixels. From that, we can project it into the world because we know where the drone is, and then build a 3D map. And then this 3D map allows us to integrate some of this information over time. So if an object, say, is a little bit difficult to see, then based on the previous frame that we saw it in, we can keep track of that information and build a better 3D map based on all that temporal information. If anyone has questions as we go along, too, feel free to ask. So this is showing our current system on the same video. So the bottom now, this is the depth map that we get out. And again, we're just projecting this into 3D space. And so we have dense depth at every point. In particular, a lot of these are pretty difficult branches and foliage of the trees. But having this dense map really allows us to build a great path planning system on top of it.
Are you using just two cameras at a time to get we have like paired cameras, whatever one's best to, for whatever object?
Yeah, that's a good question. I guess what I can say is it varies a little bit. I can't go into detail too much, but we do have overlap on the top of 3 cameras, and that can be helpful in some situations. For example, if you have a perfectly horizontal wire, then if you look in 2 cameras that are in line with the wire, you can't tell what depth it is because the match is along the row is perfect in that way. But if you have the 3rd camera, that allows you to have some, you can figure out what the depth of the wire is. So having 3 cameras is helpful over just having 2 in certain situations.
But even that with the 2, it's a lot of computing power to be able to resolve the depth. In, I don't know how many, 20 milliseconds, whatever you
Yeah, it is. And that's a challenge generally of the drone. If we have all these different pieces of the system, we want them all to work online in real time. And having that happen is, one of the bigger challenges. So on board, just for the information, is we have a Jetson TX2, which is a relatively beefy mobile processor, similar to like higher-end cell phones. Has CPUs and GPUs on it. So if you have efficient GPU code, that can help with some of these things. Also, figuring out efficient ways to use your computation. There's a lot of data coming in every second. Processing that all equally isn't really efficient, and so figuring out the important places to place your computation and so that you can only focus on those areas more is helpful, and so doing that smartly helps a lot. So given this, it looks pretty good. So what are the problems that we're facing? So this makes it seem a little bit rosier than it is sometimes. There are a lot of challenges that still occur in stereo. So this gives an idea of some of them. So on the top left, something that is extremely common right now as it's winter is thin branches. So you go outside, there's thin branches everywhere. And if you want to run through a forest, they can be really difficult to see and really difficult to avoid. In the top center, there's here both sun glare, which can make it extremely difficult to get good stereo, and also there's happens to be a smudge on one lens, which makes the sun glare much larger. The top right is motion blur, so if you move fast, especially if you're rotating really quickly, then you can get blurry images, which corrupts some of the image data. Reflections are really difficult to deal with because you can see the image perfectly, but the problem is that what you're seeing is not geometrically what's in front of you. You're actually seeing the reflection off something behind you. And so if you estimate the depth, you'll get a great depth value, but it'll tell you that it's farther away than it is, and you can run right into the mirror glass here. Textureless surfaces are also difficult because you just don't have the texture there. You don't have the information in order to get good stereo matches. And then finally, when you're out in the real world, just dealing with things that happen, such as water droplets on the camera, and being able to gracefully deal with that and get good depth as you're able to is definitely still a challenge. One thing that's helped with that is moving beyond some of the classical pipelines of stereo that I kind of described before. If you're able to use more information, so first of all, semantic segmentation, which I talked about some, but maybe you're able to classify a tree and you know that might have a lot of thin branches, and so you might want to fly farther away from that if you're able to. Or we also on the drone have temporal information, and so making use of multiple frames can help disambiguate certain situations, or things that you can't see in one stereo frame, maybe you can see over multiple, and so that temporal information can help a lot. We also make a lot of use of deep learning in some of these systems. We had a paper back, I think 2017 now, that was an ICCV, a computer vision conference. Since then, it's gotten much faster and better, and we're using a lot of these systems on the drone today. And so that was some of the results you saw before were from these sort of systems. This is showing just some still frame examples of our system running on some particularly difficult cases. So first, dense foliage is difficult in its own right, but then also figuring out some of the separation between branches. You can see there. In the middle, we're showing power lines, which are difficult to see. Even here, they're not perfect. You can see this power line in the middle. As you go farther away, it kind of fades out, and we don't see a little bit of it. So this is definitely not solved, but shows some of what our current system looks like. And also indoors, when you have white walls and difficult confined areas with little texture, this is showing some current results on that. And this has come a long way since our first flight using deep stereo vision. So deep learning for stereo is really powerful, and we first flew with it in 2018. On the left here, this is showing a collision that we had around then, where we see this branch that we ran into when we play back the log of when we flew, but it's spotty, and you can tell we don't really see it until the last minute. And on the right, this is just showing some obstacle avoidance with this system. Again, it's improved since then, but was working as of about July 2018. This is showing another little bit difficult situation where I'll just loop it. Right in the middle, there's some thin branches that we see, but you can see that they're a little bit temporally inconsistent, so they kind of flash in and out.
Why is that a terminal event?
Oh, it often is. You mean this one on the left? Yeah, it depends on, I guess, the thickness of the branch and how we hit it, but it can be. Sometimes, depending on the crash, it's able to recover. So we have something that's also new about this drone is we've completely redesigned the planing system, which we're going into maybe a little bit later in the talk with Anurag. But it can often recover from situations when it's been kind of disturbed pretty violently. Where it can't is if it hits a branch and then a propeller breaks and a camera breaks and an arm falls off. That's a problem. So it depends on the crash a little bit. Yeah. Just another video showing 3D obstacle map with some complex foliage here in the tree. And one more again with an enclosed space and showing that we're able to see the walls despite their texture. So this is something that's really powerful about using a deep learning based system is that even on textureless surfaces, if you can figure out that you're indoors and this is a white wall, then you can fill in that wall and get a good depth. Yeah.
Did you by any chance experiment with IR patterns to target this problem?
Sorry,
Did you experiment with IR patterns to target this problem of textureless surfaces?
we haven't too much. No, I mean, so our system is mostly just pure camera and.
I mean, IR patterns to create textures on textureless surfaces.
Yeah. As far as like, yeah, I know what you're talking about. Those work more indoors. Is that right? And so I think we focus this to really be more general. And there are some other sensors like using an IR camera or using radar, like an ultrasonic sensor, something like that would help in certain situations.
Then, like, use the camera only, because the IR pattern creates texture on the surface.
Yeah, I think it's definitely trade-offs that having something else on here for just those situations would add complexity, and it's something that we are mostly able to address with cameras. It's a hard problem. Like that's something that Skydio, I think, is really bet on is being able to use computer vision to solve these difficult problems instead of integrating different sensors, because that allows us to have something that generally works in kind of all different situations. Yeah, so I'm going to talk about one problem that's a real-world problem in a little bit more detail. So this is dirty camera detection. When you give a real product to users, often you get dirty cameras. So this is something that in a lab setting you can clean your cameras. In a real setting, you want the drone to behave smartly no matter what happens to the cameras. And so here's kind of one way that I'll talk about that we dealt with this. So nowadays you could use also some more deep learning based methods, say labeling dirt on the cameras and so on. But we have some pretty strong classical stereo constraints that we can use to get pretty good estimates of dirt on the cameras. So this is an example of a stereo pair. On the left here, there's a big smudge on the camera. This is from a real log, a real example. On the top, this, at the time with that system, was our estimate of the stereo. And mostly the bad stereo is filtered out, but you can see this red speck. It thinks something is really close to it, and that's going to be a problem because it's going to try to avoid that. And so what we can do is basically do a really dumb stereo algorithm. So first of all, we observe that smudges generally take up a lot of area on the camera, so we can downsample it a lot, and that makes the algorithm a lot faster. Then the idea here is that the smudge kind of persistently changes the brightness of the scene. So if we look at a good pixel that's not smudged, say the one here in the crosshairs, if we look at the same row, again, these are rectified stereo images, so the same row, we can look along the row and see if there is any good match. If there is, that's great. And if there's not a good match, say down here on the smudge where this pixel is much brighter than anything in the same row, then it might be smudged. Of course, on one frame alone, this is not a great signal. You're going to have a lot of noise. But because smudges are persistent across time, you can integrate the signal over time and get a pretty good estimate of where the cameras are dirty. So this is showing an algorithm working on this scene. The top right is at every frame the instantaneous estimate, and on the top left is integrated over time. So as we move around a bit, we start to get a better and better estimate of where the smudge is, even if on some frames we don't. And that allows us to do smart things with it. We can then mask out the stereo that is bad, or if it's bad enough, maybe warn the user that they can't fly safely with obstacle avoidance. So another thing that we run into a lot is sun glare. So this is difficult because it's not a real object in the world. You just have this glare that shoots through different cameras. Using a deep learning-based system, one powerful thing we can do is try to teach the system to automatically deal with sun glare in a smart way. And so to do that, we actually have implemented some synthetic sun glare where we, using code, simulate light diffracting through a lens with imperfections on it, and those imperfections cause these sun glare-like patterns, and then we can put them in images. So on the right here, this is, you can tell a little bit, but the one on the left is the real sun, and the one on the right is a fake sun, but it's fairly convincing and helpful for training data where we can add suns as needed. Cool. So with that, we're going to talk about a little bit of object tracking and motion planning. And Anurag's going to go through that part. Any other questions before I switch over on this? We can have time at the end, too.
Cool. Yeah, so I'm Anurag. I work on the motion planning team, but also work pretty closely with the object tracking team. So here's a quick video of what the drone sees when we follow a subject. So that's Jack, one of our other motion planning engineers, running around a park near our office. So you can see that we have an estimate of velocity. We're keeping a history of where the subject's been. And one of the cool things is because we have a great visual inertial odometry system, we can see where the subject's been, and we use all of this information to predict where they're going, which will help us create a smart plan for where we should fly our drone to take good footage. So this video is kind of old on R1, but a lot of the same ideas are still being used on Skydio 2. Yep. So a lot of people were asking about multi-object tracking. So here's a demo with actually our founders trying to break our system. So they're the drone's trying to track Abe, and Matt and Adam are also there trying to provide occlusions and break it. But the drone is able to figure out who is who, and the drone tries to distinguish who it's tracking, who it shouldn't be tracking. Yeah. And we're always trying to improve, so we often try to break the system. So here's Jack again, breaking our system by doing a nice roll on the ground. But we've since been able to improve, and we can handle this case now. And there's still some unsolved problems. So for example, here you can see that we are able to get a switch between two subjects. One gets occluded, so he runs behind, and someone pops out at the same speed on the other side that looks pretty similar, and we switched between the two. So there's always unsolved problems here, and we're always trying to make the system better and better, but yeah. Cool. So thanks to the perception team and the motion and the object tracking team, we get a lot of perception inputs into the system, and a huge problem is figuring out like what should we do in order to accomplish what we want to accomplish with the drone. What action should we take? So at a high level, there's like the perception inputs. We have the state of our system. We have high-level objectives, kind of specifying what we want the drone to do, and we have a model of how, like, based on the actions we take, what will happen next in terms of the state of the system. So does anyone have ideas on what kind of objectives you think would be useful for an autonomous drone like ours? Don't crash. Yeah, that's a good one. Any other guesses? No, all right. So we have over 40 objectives that we're trying to always, make a plan for that gives us good things. So one thing is smoothness. We want to make good footage, right? We don't want the scene to be jerky. We want to stay a specified distance from the person we're tracking. Like I showed in the app, you can specify which angle you want your shot to be from, so that's something we care about. We try to take good cinematic video. We try to follow things like the rule of thirds to make the video pleasing to people watching it. So we care about where the subject is in the frame. And then, obviously, we don't want to crash, so we want to stay away from all the obstacles. Yeah. So the system here is, the main thing is you have to specify an objective, right? The thing that we want something, we want the drone to do something, we have to codify that in a set of objectives. And then you pick a way to minimize the cost of those objectives. So there's a bunch of different ways that we've tried and have done. Here are some of them. And then you do this again and again and again in real time, and we keep refining what we want the drone to do based on what we saw happen. So we pick a set of actions, see what happens at the next time step, and then redo this whole thing again and again. So on our system, we run at 500 iterations per second. We're always trying to refine and see what actions we can take to accomplish our objectives. So here are some videos of the drone planning through some complex environments. So you can see how the drone is following a subject down there through this complicated depth map. This is actually from the same example of the mountain biker riding on that scene. Yeah. So in addition to just planning, there's a lot of things that happen in the real world. One is wind, obviously. So we have some online wind estimation algorithms that are always trying to estimate like the direction and strength of the wind, so we can take that into account when we create our plans. So here you can see we're flying around, and the big red vector there, the little harder to see red vector is the wind vector, and then the dark red vector is the velocity vector. So we always have a real-time estimate of which way the wind is blowing. Yeah. I can't talk too much about how we do it, but it's not images. Based on like the dynamics model of our vehicle, we're able to disambiguate what is being caused by things outside of our control, like wind and other things. So one of the other things we estimate, great segue, is collisions. So with really clear windows, it's really hard to get depth measurements, and we see right through them sometimes. So you see in the voxel map here, there's a nice hole that we're trying to force the drone to fly through. But we're able to estimate when the drone has collided with something in real time. And you can see we fill in our voxel map with voxels so we don't attempt to make the same mistake again. Yeah. So another really cool thing that we use on the motion planning team a lot is simulation. So we really value being able to decouple parts of our system. So we're able to run just the planner without any of the perception in the loop. In simulated environments. So you see here we're doing like a nice subject follow scenario in this fake world that we've created, and we're able to use this to benchmark the performance of all of our systems like decoupled. So here's like on the right, these are a bunch of plots of subject follows through dense trees, and we're able to look at our performance over time and see how the performance changes based on the changes we make to our code. So we try to use this to keep our system getting better and better, and also catch when we make a change that makes the system worse in some cases. So another big thing is fault handling. So like Ryan was talking about with dirty cameras, we try to bake in intelligence into the system to handle like real-world challenges, but sometimes we want to warn the user. So a lot of these faults here, we will tell the user that they need to take some action. For example, if the cameras are too dirty, we'll tell the user to land and wipe the cameras. Or if it's gotten too dark outside for our vision algorithms to be working well, we'll warn them to land. And similar, we have all these different cases that we're always like trying to detect for and warn the user that they need to take action. So part of that, we try to make our system robust without these things. So here's a case that we call the inverted pizza toss. So this is the vehicle. It's upside down. It's like being thrown up in the air, and it's spinning. And it's a really hard situation for us to recover from, but this is an example of like the planner being able to plan a safe flip back before it hits the ground and into these obstacles. Another thing that we work on is propeller failure handling. So here we fail one of the propellers, and you can see that we lose authority over the yaw axis of the vehicle, where the planner is able to figure out that it's lost one of the controllers it has, and it's able to give up yaw authority, but still maintain XY tracking. So here you can actually see we tested in sim that you can still follow a subject with one propeller missing. So there is that purple box is a simulated person, and we're able to follow. You're not going to get great video spinning around really fast, but it's just to demonstrate that we still have good control over the vehicle, even if we lose a propeller. Cool. So next I want to talk a little bit about the way that the user can interact with the drone. So here's Jack again, who we love to show in this presentation, flying 4 drones at once. These are R1s. And you can specify an angle relative to the subject that you want the drone to stay at. So we've specified like 4 different angles, so you can see like 4 different viewpoints of Jack from each of these drones. So here's some more examples. Like this is side mode, so we try to stay to either the left or the right of the subject. And here we're showing the voxel map in real time. You can see that we're avoiding trees, but also keeping the subject in frame and staying to a specified side of the subject. We also have lead mode. So this is, we want to stay in front of the subject. This is a video that we've like hyperlapsed, but you can see Adam on his run, and the vehicle stays in front to get you like a nice frontal shot of the person. We also have some like things that we call one-shots. So these are like canned motions that you can just execute with one tap on the app. So we call this a droney. So the drone will fly out and take a really nice cinematic video of you and your buddy standing on this ridgeline or wherever you happen to be. So these are all really powerful tools that we try to enable to all the creators using our drone. And the really cool thing is obstacle avoidance is always running. It's always trying to make safe plans, so you can kind of take more creative control and let the vehicle do the hard stuff of flying through things. So this is cable cam. You can set like 2 points, point A, point B, and we'll make smooth video interpolating between the 2 points, but at the same time, we're always avoiding obstacles and making sure the drone is doing safe things. Cool. So I wanted to talk a little bit about some other parts of our system other than the autonomy. So a big thing is the mobile team. So we have 3 ways to fly. We have the mobile app, which we have on iOS and Android. We have the controller, which extends the range, gives you a nice like tactile interface to fly the drone. And the really cool thing is obstacle avoidance is always on, even with the controller. So you can fly these crazy trajectories, and the drone will make sure that you're not doing anything dumb to try to crash it. And then we have Beacon. So Beacon has a GPS sensor in it, as well as an IMU, and we're able to combine visual tracking with GPS-based tracking. So like you saw in one of the earlier shots, even if you get occluded by trees or whatever you run in between, the drone can keep estimating where you are and smoothly blend between visual and GPS tracking to keep you in frame once you come out from the other side of the occlusions. So one thing that we care a lot about right now is interface. So we have people and all these controllers and ways to interact with the drone, and we have our autonomy system. And one thing we're really trying to work on right now is to make that interaction as easy as possible, as smooth as possible, and we think there's a lot of room to like innovate here in this space. So we're definitely looking for people if you're interested in working in like the intersection between like people and robots. Like we think it's a really cool space, and we're working really hard there. So a little bit about the mobile tech. So iOS and Android, they're all written in Swift and Java respectively. But one of the cool things we do at Skydio is we have a common C++ core between those two apps. So the way that both apps interface with the autonomy system is the same, and we have that all written in C++, which allows, like myself as an autonomy engineer, I can contribute to the C++ core and have it work with all of the other things that are written in Swift and Java.
All right, stand there.
Sorry, what? Does someone have a question? Okay.
All right,
So
stand there.
this is Sam, one of our founder's daughter.
Press and hold the blue button to take off.
Flying with Beacon, she loves it. Like, she can take off, she can fly it. And we think it's really cool that literally anybody without much experience can fly our drone. Which I don't think many other drones, it's like really hard to fly a drone traditionally and very stressful. So I think this is super cool.
Press the button and then wave your arms around. Go like that. Wave your
So we have a feature called point and shoot.
Point at the drone
So if you
with the
hold
beacon.
down the button on Beacon and point somewhere in the sky,
Alright,
the
now
vehicle
turn in
will
a circle.
fly there. So this is what he's
Yeah,
trying to
look at
demo through his daughter.
All right, run, Sammy, run. It'll follow you.
Yeah, cool. All right, switching gears a tiny bit. There's a few other roles we're hiring for that I wanted to touch on. So one of the things we're hiring for is the embedded team. So we have 9 microcontrollers on this vehicle. So we have a signal processor that handles the main user camera. So it's a Qualcomm chip. We have the NVIDIA TX2, where we run all of our autonomy core code. And then we have a couple of other lower-level microcontrollers. We have a gimbal controller that handles stabilizing the gimbal, a flight controller that allows us to decouple some of the lower-level controls. So if something bad happens and we lose our NVIDIA TX2, we can still maintain XY control, we can land, we can do all these things on this lower-level system that allows us to be more robust. And as well, we make our own microcontrollers, write custom ESC firmware for controlling the motors. Yeah, same things here. And then not only on the vehicle, but we also have embedded stuff on each of these. So we write custom firmware for the beacon, the controller, and the chargers and the batteries. Yeah, question?
Is there a reason you guys decided to go to make your own flight controller rather than go with an open source?
So the thing about Skydio is everything on the system is designed with autonomy in mind. So we try to make everything, it's really hard to fit everything in this really small form factor if you don't make everything yourself. So the way that we interface with our cameras, everything is all custom, and we designed it with the entire software stack in mind as well, which is usually why we make those decisions. We also are hiring for the platform team. So the platform team interfaces the drone with external APIs. So we have an API that you can send high-level commands to the drone. You can build apps on top of what the core autonomy features of Skydio 2 are. And they also deal with a lot of stuff like getting telemetry data back from the vehicle so we can debug when things go wrong. They provide the simulation tools that we use, as well as maintain the SDK between skills, which is this high-level layer where we can write functionality like the drone you saw. That's a skill. And they also provide the SDK to the mobile team to specify commands on the vehicle. The platform team also handles some stuff off of the vehicle. So for example, the manufacturing is all done in Redwood City, and they write all the tools to make the manufacturing process easy. They also maintain all of our internal developer tools and work with other companies to help them integrate with our system. Cool. So we're hiring. Thank you for coming. We're happy to answer any questions any of you have. Just go to skydio.com/team for all of our open positions, and we're especially looking for people in these roles here. Yeah, that's all we have for you today. Thanks.
Why do you have a 3-axis gimbal?
Yeah, so being that third axis, the yaw tracking, helps us get even more stable footage if there's any yaw tracking error in the vehicle. So we found that really helps smoothen out the footage. Sorry? So I can't get into too many details of how we do it, but we've worked with both of those approaches. Yeah. Yes.
Would you be willing to say whatever you're allowed to say about the cameras? I know there's 6, but what kind of cameras are they?
Do you want to answer that?
Yeah, I mean, I can say because they're hardware. I'm trying to remember exactly the details. I mean, they're 200-degree field of view, color, rolling shutter cameras. I think they're mostly an off-the-shelf module, and that they're not like too customized. They're similar to other cell phone cameras. Yeah, but they're 4K color rolling shutter.
Gotcha.
I have a question about your simulation with the failing propeller. So that is only simulation, right? You haven't tested out the story because it will surely break your VIO.
Yeah, so those are both, sim scenarios, but things that we're working on.
The other is, it's rather common. You said that in your mobile app, you had common C++ core, and then people write other stuff. So there is another company who had the same structure, and they switched back, which is Dropbox.
Yeah, I heard about
C++
this.
core, and then they ended up just getting rid of that, and then just writing native on each platform. And the reason they say they did that is because it's very hard to hire high-quality C++ programmers.
Yeah, it's interesting. For us, it works really well because we write all of our autonomy software in C++, so it's easy for us to also contribute to like this core code because we don't have to learn Swift and Java ourselves as autonomy engineers. So I think it works well for Skydio, but might not for everyone. Yeah.
For your VIO system, how much of that is like totally in-house custom? How much of that is prior?
It's all in-house. Like we make use of algorithms that are similar to those that have been described. Like we didn't completely invent VIO from scratch, but we're not making use of open source systems. Yeah, it's all built custom in-house.
So like, are you using classical methods like feature extraction and then like back?
There's some. It's a bit of a combination. Like I think deep learning has a ton of power. Some of the ways to make it work well for more structured problems like VIO. There's still a lot of, I think, research to be done. We make use of a bit of Haskell and deep learning in that system.
Is that running on the Jetson?
It is, yeah. Everything is running on board the German.
Well, I meant as opposed to the ST controller that you were talking about.
Yeah, it's on the Jetson. Yeah.
Okay.
Yeah, one more up there.
Good question. I know since you're not using it sort of like, you're only computer vision, obstacle
Right.
why is that?
LiDARs are heavy and expensive, especially for drones, especially for consumer drones. And we think camera technology is getting better and better and cheaper. So Skydio kind of made a bet that computer vision is the way to go.
Oil prone to flares and prone to the sun.
Yeah, that's true, but it's also expensive and heavy and probably won't work well for a consumer drone. So.
Yeah, in some sense, like, if you look at these images as a person, you can tell, like, oh, that's a wall or that's a water droplet. And so these are solvable problems. They're hard problems, though, and so getting really good people in computer vision, machine learning, and figuring out the right way to do it is the challenge. But if we're able to do that, then using cameras that are much lower cost and can work in different environments is really powerful.
Regarding the sun, it's not something that you can solve because even a person who wants to see the sun can actually navigate because you're kind of blinded with the sun. So it's not something that you can possibly avoid.
Yeah, no, I agree. Yeah, like if you can't see in a direction, then you can't see in the direction. But maybe you can do smart things with the information that you have, like not fly in that direction or tell the user. But you're right that, like, for example, if you're completely camera-based, then if it's pitch black out, you can't do a lot. And so then you either need lights or some other sort of sensor in order to work in that situation.
So what are your biggest failure cases right now that you guys are working on or experimenting?
I mean, I can speak to like, so I work on dense mapping, which an obstacle avoidance. I mean, thin branches are like the worst thing ever. Like, so this time of year, like flying through a forest with lots of thin branches when the sun is low and there's a lot of glare is really difficult. And so basically all the situations that I said, and we've improved a significant amount since our first product in a lot of these difficult situations, but it's nowhere near fully solved. And, we want to fly, safer and faster, and once you start getting higher speeds in a lot of these situations, it's become that much harder.
The other cool thing is we have a lot of customers out there using it, and we get like issues back, and we're able to triage and work on those things thanks to our like data pipelines. They can upload logs to us, and we can diagnose. Yeah.
You mentioned the maximum speed that you can achieve. Is that limited by the hardware, or is it limited by like the quality of your estimation mapping?
It's a little bit like the speed that we've allowed people to fly is what we think things are safe at right now. Yeah.
How far can you follow someone from? I know you were adjusting like this, like during the demo, you were adjusting like how far you're following them.
Mm-hmm.
Like, is there a range for that? Is it limited by like the vision of the subject, or like even if the subject's like a tiny little dot?
Yeah, so things change a little bit when you have a beacon. So because beacon has GPS tracking, we're able to track from really far away. So there's some dronies where you can get like several hundred meters away from the subject, and because we have GPS tracking, we're able to keep following them. But you're right, if you're seeing a little speck in the image, it's really hard to detect that. So it's a combination of if you have GPS tracking, will allow you to get further away. Yeah.
Regarding your path planning, are you doing full dynamically feasible planning at 50 hertz, or are you generating a strategy and then hopefully?
Yeah, so again, I can't get into details on how we do this, unfortunately, but if you want to learn more, you should apply. And, and then I'll tell you all you want if you join. Yeah. Cool. All right, we'll be up here for a few more minutes if anyone wants to come down and talk. But yeah, thanks everyone for coming.
research engine will continue to work on this stuff. It's just move on outside this. Yeah, we can do it with one camera, and we can help you with that. Yeah.
Yes,
I guess it's still the case of just like the guys, it's pretty much closed off.
Like, you'll know what I was installating. We're in the war now. But even then, it's a, yeah, it's a button that follows you around. It's on it or like, there's nothing interesting. Like, make it more available. Click OK.
Same issue.
Yeah, they've been ordering more.
That space is involved in fast. Yeah, that's just.
Where do you get all your data from? Yeah, that's like just like
yes, we have thousands of
but then you need the data about our data. You have to do that all around. I really watch it. Seems like it works reasonably well.
Right.
Okay. That's like, that makes me very upset. Are you playing it?
Yeah, I said, I mean, if you have that stuff, you know, what,
so we do publish some data.
Yeah, I looked at your publishing record.
Something that
It is mostly realistic enough. Okay, so the answer is that you plug something in. So are you concerned with a lack of like coverage? Like it might really work well in like you're based in Redwood City, like California. Are you
so we have a couple of things. One of the interested in
are there guys that are customers?
both times like super helpful.
Two.
Two, I want to find ways to improve it.
I see.
Second,
yeah,
how do you out there?
this is something that we remain heavy.
So do you keep full data logging on the Okay, that's nice.
Yeah, we don't get it unless
Eventually, we all know.
Okay.
Tomorrow.
Right.
Right.
Are you
Well, also for,
all of it, right?
yeah, for you, if you're watching people kicking off the project, you don't do
Yes, there's storage on board.
Because that's the, I remember what's here.
Yeah, even if
All the data is still super expensive. Like it's like, oh, it's really like 30 gigabytes.
let's do it. So yeah, we'll see.
Okay.
I've heard a lot of comments. Yeah. I was like, oh yeah,
First thing you were doing there was
rats.
first
One of
thing.
my friends. I said right here. I want to see.
Actually, I had a question about, so when you're doing motion planning, how much like a risk do you incorporate into like your error bound, your localization, or like this optical
Yeah. So there is some stuff that's like
The 3D compilation stuff, yeah, when you would
was really good.
That's what I'm struggling with trying to get a good balance on.
But yeah,
So is there any like
We had
notion of like Google history, and you kind of went over this with the wind almost. If you know that it's a windy day, then you might be more like
it's all
what is it like? For example, diagnosing not a fully broken cell, but one that
So yeah, so we're always trying to estimate like what external things are happening.
But you're finding just dynamic space, or is it like the ability to follow the time? You just never going to assume that.
Yeah, so it definitely it has a dynamics model, and one of the things so Ryan mentioned it. So we improve on it's something that we it's really helped.
Yeah, so you're there, Garrett's there,
And you mentioned some of these reflexes which you have.
So, okay, so
Do you incorporate potentially having to go into a reflex in your mind?
First of all, thanks for calling about your coffee. My question is, the first revision, right? But now we have.
let me know.
Why? Is that you guys have questions? Sure, yeah. Oh, it does. I don't know if either of us are embedded people. I don't know if I can watch it all, so it might be better. Yeah, sure. That's all I have. We are hiring both plenty of internships across the different software. So we have a resume. Oh, okay. Also, I would, if you go to our website, we have applications for it. So I would apply on there as well.
Yeah, we really, especially on the autonomy team, people we write everything in Express, so it takes, it's hard, it sounds pretty easy, what you're saying, right?
Yeah, I'll see if make a note and I would apply on my website. And you can also follow up if you want to hire this guy. Yeah, so I don't know if it's standardized or not, but about we're small enough that it can be very. Nancy,
The thing is,
Yeah.
do you know if like
really cool
internships are usually a certain length?
motion planning things is important. So we're able to touch everything from high level segmentation.
Yeah, so yeah, Skydio got that team if there's.
As a member of the planning team,
I'm hiring. Yeah.
every day is
Yeah.
good work.
Yeah. Yeah, we could definitely, so, yeah, we're definitely not embedded, but we could. Hiring at Skydio, where I'm Ryan.
The position was like,
Ryan at Skydio.
is it sensing from the camera and using outside?
She's our help with recruiting.
As I mentioned, decouple our system. That's just testing support.
read over some of the classical papers that have been published.
Yeah. Simulation